Hello and welcome to this fourth video in the lecture on the hash-based crypto primitives. In this video, we're going to wrap up our discussion of SHA-512 by digging a little bit deeper into the F function. So remember that for SHA-512, we have blocks of the message. Say, I'm going to draw two of them here, mi and mi plus 1. This get fed into some hash function f. So there's a hash, the same hash function is applied to each and every block. And the second input to the hash function is the message digest of the hash code from the previous block. And then the output of this hash operation h sub I gets fed as input to the next one, and so on and so forth. So what we want to do in this video is to look inside that box. So I'm going to draw that box pretty big right here. So again, this is supposed to be the f function. So what are the inputs to that function? Well, first we have the previous message digest coming in, and we also have the current block m sub I. Okay, so the first thing to realize is there will be 80 rounds of computation, which I'm going to represent here as ovals. So here is one round number 0, round number 1, dot, 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 round number 79. So let me label those. So these are going to be rounds of computation. They are not data structures or buffers or anything. In fact, there's only one buffer in this algorithm, and this buffer will be of size 512. Notice this is the size of the message digest, so 512 bits. And this buffer is going to be split into 8 subbuffers like this. And the subbuffers are called A, B, C, D, all the way down to H. So we have 8 buffers, each of which is 64 bits. So we have a total of 512 bits, which is the size of the message digest for SHA-512. So the first thing to realize is the buffer is initialized to the value of the previous message digest from the previous block. And for I equals 0, we have h of 0. Since there's no block before block number 1, this is equal to the initialization vector. And this initialization vector is built as follows. You take the first 8 prime numbers, okay, 2, 3, 5, etc. You take their square root, take the fractional part, convert that to binary, and grab the first 64 bits of the fractional part, and that becomes the first initial values of the components of the buffer. Okay, so this is the first step, is the buffer is initialized in the first execution of f with the initialization vector, and for every other block with the previous value of the message digest. So there's only one such buffer, but every round of execution is going read this buffer, do some computation with the values, and then rewrite the buffer. So this is true for round 0 and then for round 1. So notice what round 1 reads is the state of the buffer after round 0 has modified it, and so on and so forth until round 79 reads the buffer in, does some computation, and modifies it again. So to be clear, there's only one buffer. These are not buffers. These are just computational rounds. Now notice there's some inputs missing to the rounds here. First of all, there are some hard-coded constants for each round. There's a constant K0. For round 1, there's a constant K1, etc., etc., K79 for round 79. So these are the constants mentioned here. The way these are initialized is you take the first 80 prime numbers, you take their cube roots, convert that to binary, and again, grab the first 64 bits of each of those, and that gives you 80 constants. Now, one more thing to notice is so far we haven't used the block itself, the message block. So the way it is used is as input to the round function in the following manner. First, the block is fed into a message scheduler. And this is very similar to the key scheduler in DES. This message scheduler is going to take the block and is going to generate 80 different values, and these will be dependent on the contents of the block. So this is going to be called the word 0 fed to round 0, word 1 fed to round 1, and so on all the way down to word 79. So now we have a pretty complete picture of the F function. It's going to take a block, and the previous message digest is going to initialize the buffer with that value. It's going to generate words W0 through W79, and then it's going to execute 80 rounds, reading the value of the buffer, inputting those two other values, mixing the bits, and overriding the buffer. In the next round, we'll do the same thing with the new value of the buffer and the other two words, the constant and the message block dependent one. So what is the final output of the F function? Well, remember, this is the value of the message digest for the next block, so H sub I. And the way this is obtained is first you will grab the 512 bytes from the buffer at the end of round 79, and then you're going to grab the value of the message digest of the previous block, and you're going to go and add those up in a particular way. But at the end, you're left with a 512 bit value, which will be output to the next F execution. So this is what is explained in this text. I'll let you pause the video, read the text a little bit more detail, and match it up to the drawing. And after that, I'm going to show you a different way of drawing the same F function. Notice in this function, we're not drawing the buffer, but we do have the rounds and the message scheduler and the constant values and the word values, and then the previous and next message digest. What I like about this picture, and the reason I included it, is because it gives you a little bit more detail about this addition step that I showed you over here. So remember, you're taking two 512-bit values, adding them up, and forwarding the output. So the way it's actually done is that these 512-bit values are split into, again, 8 blocks of 64 bits. The first 64 bits are the result of adding the first 64 bits of the buffer and the first 64 bits of the previous message digest. So you take the A part of the buffer, the first 64 bits of the message digest, you add that up, modulo 2 to the 64, so you ignore the carry out on the left, and that gives you the first 64 bits of the output. Then for the second 64 bits, you grab the values of in B at the end of round 79, and then you grab the second group of 64 bits from the previous message digest, you add those up, modulo 2 to the 64, and that gives you another 64 bits. You do that 8 times, concatenate those into a 512-bit string, and that is the output of your F function. So this concludes my presentation of the SHA-512 algorithm. Notice the only thing we have not explained is what happens within each round. The computation are exactly the same, but there's a bunch of and OR and NOT and XOR and bit shift that happen. And so since you're going to have to implement this algorithm for your next assignment, I have assigned a reading assignment that explains in detail not only the overall algorithm, but also what goes on inside each of the rounds. So with that, with this video, this reading assignment, and the comments that will be included in the code handout for the next assignment, you will be able to implement this SHA-512 algorithm completely.